Hello everyone. So for our second video, I just want to recap. We were looking at scale and looking at photos of scale. So we went from a park bench in a park to multiplying that and moving out by 100-fold. And that took us to a view of some place like around Morristown. And moving out 100 times, that takes us to a regional satellite photo. This one is of southeastern Pennsylvania. And then, hold on. Yep. And then we went out another 100-fold and saw the Earth from a satellite. Another 100-fold, and we can see the Earth and the Moon and some space around it. Now we're looking at now 10 million times that area of the park bench. So we're basically looking at something like 10 million park benches. Really big numbers that we're talking about. Pretty indefinable. And let's keep going. We also went to the fact that we saw another 100-fold out, and that became the distance between the sun and the Earth, about 1 billion park benches. So in continuing that and moving forward from there, now we're looking at the outer scale of the universe. And we are looking at our solar system in the next 100 times out, and that's about 100 billion park benches. Then our solar system and nearby stars, 100 trillion park benches. And I wanted to point out here, this is the sun and our planets. You can't see our planets anymore. We're too far out. We talked about that nearest star. Here it is right here, this small star right there, Proxima Centauri. And this is what we're looking at. We're looking at a view that is so far that the sun seems quite small. If we take it out another 100-fold, we finally see our galaxy as it is. And look, the sun and the Earth are one solar system out of many billions of stars in our Milky Way galaxy. That is, all of these solar systems are orbiting a common core in a galaxy. This is a spiral galaxy. The Milky Way is a spiral galaxy. We'll learn about other types as well. And in a spiral galaxy, all of the solar systems rotate around a common core. What is a galaxy? A galaxy is an island of stars. In fact, it's a massive island of stars. Massive meaning an enormous mass of matter, and stars make up that matter. It's held together by gravity. We'll learn about that quite a bit, and it has a common center, especially with spiral galaxies, for rotation. Our Milky Way galaxy is an average kind of galaxy, as Neil deGrasse Tyson mentioned. It has, we're not sure how many stars it has. We guess, it's 250 billion stars, plus or minus 150 billion. So we're not sure at all. We need a lot of exploration. We are going to move from this scale work that we're talking about in space and in time. We're going to move into the scientific method so that we can study what we don't know in organized ways that are evidence-based. We'll talk about that in a few minutes as well. A fantastic shot. Sometimes you can get this out west, and you can see here the Milky Way galaxy. We're looking at the common core there, the common center that you see right in here, and we are way out from it. And in fact, this Milky Way is stretching from the northern hemisphere to the southern hemisphere, and obviously way beyond. But in the northern hemisphere, we do get a really great view of the the central core. Now, if you would like to see the nearest galaxy to our Milky Way galaxy, we actually have a good view in September of the Andromeda galaxy, which in the northern hemisphere is our closest galaxy, the one that we can see with the naked eye. And you can see that by looking in the northeast in the evening on a moonless night. September 16th is going to be a really good time for that. Let's hope for a cloudless night. And when you look to the northeast, look for a W-shaped constellation, a pattern of W in the sky, or you can look over here for a box pattern in the sky. That's Pegasus. And in between the W and the box is Andromeda. And above Andromeda is the Andromeda galaxy, which looks like a fuzzy cloud, but it's actually the closest galaxy that we can see in the northern hemisphere. It is twice the size of our Milky Way galaxy, and the light from that galaxy, guess, takes 2.5 million years to reach Earth. Just incredible. So this galaxy was first seen with the naked eye by a Persian astronomer in 905 AD, and he wrote down his description. We know that that's the galaxy that he saw. Really amazing work. The Islamic astronomers really moved us into the Renaissance, and the study of science started with astronomy. That's why we're moving over to the scientific method, as really put into place by Islamic researchers and Islamic astronomers. If we go another 100 times out, we see clusters of galaxies together. Galaxies tend to cluster. We'll talk about gravity and that cluster. This is a cluster of, about 20 galaxies? Andromeda galaxy is not even in this cluster, but we don't see many of these galaxies with the naked eye, and some of these galaxies are seen only from the southern hemisphere. So we're talking about a distance that is 100 quadrillion big park benches. Really difficult to understand. And then finally, this is the last of what we've been able to observe, really from the Hubble telescope, is a part of the universe that shows super clusters of galaxies. These are not superclusters. Those are just ordinary clusters. And 100-fold out from there, there are superclusters of galaxies that have filaments between them and voids between the filaments. And we're talking about 10 quintillion park benches here. So, unfathomable. Now, what is a universe? A universe, as opposed to a galaxy, a universe is the total sum of all matter and all energy. All galaxies, everything in between. If you had to think about the number, well, let's back up. Hubble thinks, the Hubble telescope has been able to look into what is probably, who knows, 200 billion galaxies. Amazingly, Hubble is going to go offline and start to disintegrate in this year. It was supposed to be replaced already by the Jack Webb telescope that I actually saw being built at Goddard Research Facility down in Maryland. Fascinating. And Jack Webb is delayed. It was supposed to go up in 2018, then it was 2019, now it's 2021. And hopefully Jack Webb will be able to see us so much more than Hubble, which is just amazing. But in the meantime, you can think of every single dry grain of sand on every single beach in the entire world, put them all together, you haven't equaled the number of stars in the universe. So it's just something for you to think about for scale. I've given you many different scales here, from the Air and Space Museum and the grapefruit all the way through here and the park benches, and now we're talking sand. So I'm trying to relate scale to you in many different ways. Now you might say to yourself, well, that's 10 quintillion what? Park benches? We can put some numbers to it. And once we make an observation through a telescope or make a scientific observation, we try to apply math to it, add structure to it. So we can say here that this was 16 meters across. You probably said like feet, okay? Feet, you can use 52 feet. And you can say 52 feet times 10 quintillion equals 520 quintillion feet. That's what a universe is. And you say, well, feet aren't really good. I should really use miles. But that gets really dicey because then you start to get into fractions. Then you have to say that 1 mile is 5,280 feet, and you have to divide 520 quintillion by 5,280. It's just not going to go well. And everybody hates fractions anyway. I hate fractions. There's so much error involved in fractions. So we're going to get rid of fractions in this course and use the metric system because it's in powers of 10, and that's easy. You can just move the decimal back and forth. So making measurements simple with the metric system really prevents a lot of errors. We're going to be doing that, and we can say it was 16 meters, and now we have 160 quintillion meters. But we don't like meters, so we want to use kilometers. If we use kilometers, it's easy on metric. Look at this. So 1 kilometer equals 1,000 meters. And if you're talking 160 quintillion meters, you can just lop off the zeros there. And look, you got 160 quadrillion kilometers. Still too much. Still too much. But you know what? You know about gigameters, and you know about gigabytes, right? And a gigabyte is 1 billion bytes, so that you can take off all of these zeros from your 160 quintillion meters. You can take off all of those zeros, and now you're down to 160 billion gigameters. Right? It's looking better, but too many zeros still, so let's keep going. And you love terabytes. What about terameters? A terameter is 1 trillion meters, which is really easy to remember because trillion, tera go together. 1 trillion meters. So look, you can take off so many zeros. And you've now got 160 million terameters, which you can kind of wrap your head around a little bit. But there's still too many zeros, and you could have a problem there. And we want to not only simplify the conversions back and forth between meters and kilometers, but we also want to get rid of some of these zeros. So you should know that astronomy is the science of big numbers, and we're going to make it easier by just using those decimals back and forth, using the metric system based on the power of tens. We're going to slide that decimal and make fewer mistakes, but we still have lots of zeros. We're going to get to the zeros next. See you on the other side.